let me just say something very basic about automorphic mass forms. So I think probably all of you are most of you know it, but maybe people that only deal with the holomorphic case might not know everything. I don't know. So let me just say something. So I have an automorphic form phi of weight k, and for a group gamma, so like some group of the first kind, but let's say just for simplicity, let's assume gamma 0 eventual at 11. It will be a bit easier to discuss a couple of things later. Okay, so what does it mean? It means that well, the function on a smooth function, not necessarily holomorphic, on the upper half plane, then is a function that is automorphic. So, phi of gamma z. Well, here you could. I'm gonna just ignore the character for simplicity, but you could add a character, k of gamma, and then transform like that. Phi of z. This one for all gamma of the form A, B, C, D in your group, and for all z in the upper half plane. And then I want, well, two more things. The first one is that this function is an eigenfunction of the Laplacian. The Laplacian of weight k. So lambda k of phi is some lambda of phi. And lambda is very, well, lambda of course depends on phi. And is very convenient to write it in this form. S of phi times 1 minus S of phi. And lambda, delta k is the Laplacian of weight k, which also means it's not super common, but well, okay, it is. Which is defined. This is the standard Laplacian, but then I add another term like this. Okay. So of course, if k equals 0, you get the standard Laplacian. Okay, and the last thing I want to add is the last condition is that it doesn't grow too much at the cusps, or which is essentially equivalent. It has a Fourier function which with no negative term. Which means, well, now the Fourier transform only at infinity, but one cannot, well, one has this for all cusps, and, but okay, that's write it for at infinity, so you have an expansion of this form. So here, if S is this S here, if S phi is equal to 1/2, then you have to add the log, a y to the 1/2 dy of y. And then, of course, there is the interesting part. So this is the sum over n, and then x. X is, of course, the real part of z. And a function here that I will just ignore is basically a Whittaker function, and depending on how you want to normalize these coefficients, you normalize differently the function, but okay, it's just the appropriate Whittaker function, which, if you think of it in terms of length of the sums, this essentially, well, okay, here no need to put the m since I already put it here, but this basically truncates the sum at n equal 1 over y. Okay, so more or less.
Zero or restricted to be positive?
Here and no is can also be 0. Sorry, no. Okay, anyways, if A and B are 0, this is a Caspar. And okay, there are, I mean, what I will be interested in is these coefficients here. And in fact, very often this will be very explicit objects, although I will just keep things a bit general. So, for example, cases of this would be for the certain real analytical time series. An example would be an equal to d of n, the divisor function. Or an could be, so these are examples. Or an equal, for example, the R of n, the number of expression of n as the sum of two squares. Or, the Ramanujan tau function. And in fact, the normalization I will take will be divided by n to the 11 over 2. This is the Ramanujan tau function, so I want it to be divisor bounded. So I want it to be the normalization for me will be this one. Okay, so then there is an associated L function, which can be well, okay. Here I brought n greater than 0, but I guess one can also take in the normomorphic case also negative, but non 0. Anyway, I will be quite vague about the normalization. So you can construct the associated L function like this. Of course, this will be also dependent on the mass form phi. And it has a functional equation. And the functional equation relates, this is kind of a definition of the normalization. I normalize the coefficients so that the functional equation relates S with 1 minus S. In particular, that's why one has to take n to the 11 over 2. So this can be hidden in F. Okay, so okay, and in particular, it means with this normalization, this is also absolutely convergent on real part of S greater than 1. Okay, so okay, what are the examples? So the standard example is just a function coming from automorphic forms. So this is f is a automorphic modular form. So if f is holomorphic modular form, then phi, well, it's not holomorphic anymore. So sometimes I will probably mistakenly say phi is an holomorphic modular form, but I really means something like this. So because of this factor, it is not holomorphic anymore, but it's essentially up to a very simple factor, just a holomorphic form. Or you can take some real analytical Einstein series and for which, well, there are many examples, but the simpler standard example have the coefficients that are the convolution between the Dirichlet characters. So in particular, these are the one that gives these two. So this will be the trivial character with itself, and this will be the trivial character with the character modulo 4. Okay, and then, okay, so these are like kind of very well-known objects. And then there are the objects that are more mysterious, which are, let me see anything about this, but that are non-automorphic Maass forms. And in fact, they're all non-automorphic, but I mean not like this, like not coming from a homomorphic modular form, which are with the exception of some special example study already by Hecke related to quadratic extension, then these are the coefficients are much more mysterious of these objects. Okay, so okay. So I will. So the title mention. Yes, what's the title? Well, it doesn't mention, but okay. I will talk about the abstract mention, the distributions of objects. So let me say something about the distribution of L itself. A lot of people have studied the value distribution of LPS. So, or to be precise, of the logarithm of LPS, because it turns out that LPS is log Gaussian, so the log of L behaves like a Gaussian. And a lot of people studied the distribution of log, let's forget the log. It will be a log Gaussian, or the log will be Gaussian. So L phi, let's say, for example, 1/2 plus IT as, so this is a set of values, as t vary between, say, 0 and t, capital T, or other variation of this, like L phi 1/2 as phi varies, or so the central point here, there is a multiplicative twist of n to the it essentially. Well, something I didn't say, but I'm sure you know, is that L phi can be analytically continuate to the complex plane, like, well, at least meromorphically continuate. One can also consider, if one twists this by a character, a quadratic, any character, or also quadratic, a family of quadratic, but let's say all character modulo a certain Q or of conductor up to a certain point, many variations. So there are a lot of people that study problems like this, the distribution of the values of these in these families, and now these are very well understood and with a lot of connection with conjecture that come from Anders matrix theory, basically. But the basic conjecture for at least for the moment, but for this then, for the distribution of the logarithm, it comes much before that. It comes from result by Selberg in the 40s, which in a particular case of the Riemann-Zeta function, but in fact a lot of this idea extends also to this. And well, then there is the result on this specific, well, on this and generalization of this by Bombier and Hegel, and a lot of result about distribution of these objects. And all of the result comes from the fact that I will be very hand-waving, because here this one will have let's say 1/2 plus IT, like in the first case. So, okay, something I should have said here, that here we take phi to be a Hecke form. We want the coefficient to be multiplicative, because in this case, then this has an Euler product in Euler product, and then well, okay, something like it's not exactly like this, but something of this form. I'm just writing the first term with put the plus here by Taylor expanding. And the point is that when you take the log, and of course this doesn't converge in 1/2. I'm being extremely unwavering here. But to some extent, this holds on average over T, pretty much. And for distribution results, you only care about that. Log phi behaves more or less like a sum over AP of AP to P to the 1/2 plus IP. And plus some other terms that actually of the order 1 over P, which actually have an influence on the mean of this object. But okay, in many cases this is just the mean will be 0 anyway. And the point is that the various P behaves independently. So as T varies, all these summands behave independently, like because the P are the log P is linear, they are linearly independent, and so basically one obtains a sum of independent random variable, which by the central limit theorem, which of course one cannot apply straight away, but something of the sort, then this becomes sum of independent. Sum of independent-ish random variable, and then this becomes Gaussian distributed. And they all work like this, all this proof, and they really heavily use the multiplicativity of the coefficients. Okay. Okay, here instead I will talk about the additive twist of L phi. So L phi of Sx is defined as the sum over n. Well, and like in the Maass case, in the Automorphic case, one has also to sum the negative. But let's skip this issue for now. So one add a twist, an additive twist E of. So this is E of an x. Sorry, I didn't say it before. E of say z is E of 2 pi I z. And here x is real. Could also have positive imaginary part, in which case this converges absolutely. But let's assume real. And this one, okay, it's absolutely convergent. For real part of S greater than 1, because of course, the modulus of E of n x is just 1 for x real. So, and of course, we can, in fact, I wrote x real, but okay, by periodicity, it's enough to take x between 0 and 1. It doesn't make any difference. Okay, so, and of course, an important thing to keep in mind is, and it changes a lot also the behavior, whether you start with the multiplicative coefficients or not, this is not multiplicative anymore. So, okay, and in general, so if one wants to understand the distribution of this object, here what varies is, one can also vary t, but then it's quite a different problem, but one would like to vary x between 0 and 1. So, if the real part of S is greater than 1, then this is, well, absolutely convergent, and in particular is also a continuous function of x. So there isn't much interesting to say about this. This just behaves like a continuous convergent series. Okay, so the interesting case is when S is less or equal than 1. And already we start with the first problem, which is here there is not necessarily analytic continuation. So, well, if the form was cuspidal, then you would have also convergent up to 1/2 with the normalization that we wrote before. But if it's non-cuspidal, then actually 1 is the boundary. And even if it's cuspidal, it converges up to 1/2 on the right of 1/2. It still doesn't converge absolutely, so there is no continuity there. So it really behaves like a random object. Confused about the way to go. Okay, I guess it doesn't matter. So there is a special point, which is the center of the symmetry of the functional equation, which I implicitly also used here, 1/2. And I mean, the behavior changes quite a bit if you take to the right or the left of 1/2. And especially in this case, if you take S to have real part between 1/2 and 1, then this problem becomes related to something that are called quantum modular form of a weight that is non-zero. And one can also study what happened in that case. I have a work with Sari Drapo about that. You can understand it fairly well. It becomes almost continuous function. There is also actually work by Paloma also a long time ago, which is related to this. This time not 20 years ago, but closer than that to 5. Okay, so so what I will be interested in is the case S equal to 1/2. Actually, I left something in the middle, which is that this maybe cannot even be continued. But if X is rational, then E of nx can be written in terms of Dirichlet character. And for Dirichlet character, you know that this one has meromorphic continuation, or typical holomorphic. So if X is in Q, so you decompose it in Dirichlet character. Each of them is holomorphic, and then you sum it back, so you get something holomorphic or meromorphic. So L of phi Sx becomes meromorphic on C, and typically with only possible for at S equal 1 as usual. So I'm interested in the value at 1/2. So for several reasons, I'll say something more. But before actually saying this, I want to add something about the symmetry of this. So these objects have many symmetries. In particular, well, basically the L phi of S, but let's say let's directly go to 1/2 of x is related to L phi of the x bar, where if x is equal a over q, then x bar is a minus 1 over q, where this one is the inverse mod q. And is one periodic, of course, this function, so what impulse you take is irrelevant. So this one is basically Voronoi summation formula, the symmetry in the central point. And the other thing which is much more hidden and is not related to this, is the different symmetry, is about the value, for example, about the values x and gamma x, where gamma is in the group. So if you define each gamma, well, this will depend on phi also, of x to be L phi of 1/2 x minus, okay, you have to put here phi gamma if you want the character, otherwise just ignore it. The sign of C x plus e with k L phi of gamma x. So this is a gamma here. Okay, so if k is even, for example, you can even ignore this. So the difference between L at gamma x and at x is a function that is continuous, and in fact is 1/2 minus epsilon for that continuous. And well, in some cases, but not always, in the holomorphic cases, is in classical holomorphic cases 1 minus epsilon the continuous, and in a special case it's much more than that, meaning it's constant. Okay, so another thing that I could have said is this one can be thought of the integral from x to infinity of phi of z, z minus x, over the vertical line to the 1/2 minus s in the, well, these are the values. If I brought the normalization correctly, I think so. Actually, I messed up with the sign. Is s minus 1. But in any case, this one is just 0 if in the case I care about. Sorry, 1. This point is 0. So this is an Eichler integral of phi. And in fact, one case, it's very famous, you definitely would know it. Maybe you already recognized it.
For h gamma, you have to avoid the point where gamma x is somehow infinity?
Yes, sorry, yes. Gamma of x. And, okay, and if you want even x, different from infinity, which I'm just saying real, but so okay. This result is also saying something about the extension. So this one is originally defined only on Q, but then it extends continuously to a function of R. And okay, so and something more I should add is that these are, at least for an appropriate definition, means that these objects are quantum modular forms as defined by Zaghe. Well, he left it vague, but if, definitely in that spirit, the precise definition. So basically the definition is something like this function here is more regular than the original object, more or less. Okay, for a certain rational, a certain function on rational, which here is healthy. Okay, so about this result is actually non-trivial. In some cases, this is essentially trivial, at least if one knows the theory of modular symbols, because for k equal to L phi of x is so k equal to phi automorphic, meaning counter automorphic modular form, and automorphic and Caspian. Yeah, then L phi is the modular symbol. And h gamma of x is actually just constant. The constant that depends on gamma, but is constant in x. So of course this theorem is trivial in that case. It's constant and thus analytic if you want. So then, like some years ago, I proved this result in the case of the real analytic Eisenstein series. With an being the divisor function. So this was proven by me in maybe 2016. Okay, so and then in the case of holomorphic modular form, I don't know if it was written somewhere before. I didn't see it anywhere. Holomorphic forms. Let's say cusp, but okay. Cusp here is not of any weight, so not just weight 2. If the weight is not 2, then it's not constant anymore, so it's a bit more subtle. But this was written down at least, basically an observation by myself and Sari Drapeau. This is Drapeau. Okay, and then this result is use the Cauchy's theorem. So it doesn't really generalize to Maass forms, whereas this one probably can be generalized to Eisenstein series. But the case of non-homomorphic Maass forms is way more subtle, and this was proven by non-homomorphic. By Sari Drapeau and Nordentoft in 2022. And also it's like I will some things. I mean, it was put in the archive 2022. It hasn't appeared yet, but okay, it's. Let's say that we don't need to archive. Anyway, so this is this closed the case. So every case is not this conjecture. Okay.
For the last two cases, they are not constant anymore, or?
No, they're not constant. They're like yes, they're not constant. In this case, it behaves more or less like a continuous function. Sorry, a nice function, or a differentiable function, say times n e of n x times n to the 3/2. So you only have one convergent extra, which gives, it's not exactly that, but more or less something like that, which gives the 1/2 minus epsilon order continuity. Whereas in this one, it's much more tricky, because basically the proof starts from this expression, and then you have x and gamma x, and you would like to, you have the function with gamma x, and then you would like, say, s equal 1/2. And of course, if it's a non-Cauchy, like here, you have to regularize it to avoid problem of convergence. And you would like to make the change of variable gamma, well, in, like changing this into x. So you have x gamma minus 1 infinity, phi of z. So if the weight is 2, this is just this. If the weight is 2. But then, okay, so you say, okay, I take the integral from x to infinity and the integral from x to gamma minus 1 infinity, I subtract it, I have an integral from gamma minus infinity to infinity, which is a constant in x, which is what happened in this case. But then there is a catch that they do not simplify, because this would simplify if you have Cauchy's theorem. One is integrating over a vertical line from x to infinity, and the other one is integrating from gamma minus 1 infinity to x. So if you have Cauchy's theorem, then this difference is just this integral here, this extra line here. But if you don't have Cauchy's theorem, then you cannot do this. I mean, these two kind of cancel at this cusp. So that's why you got the order continuity, but you have to work for it, and there are definitely some subtleties there. Okay, so value distribution of these haven't been studied since a long time ago. So some results of these were especially related to these, which are related to, for example, Dedekind sum sometimes, or generalization of them. So some of these were studied before, but in general, the distribution of this object were not studied until the 2010s. I was already looking at the case of the divisor function, because it's interesting for other reasons. And then there was a conjecture by Mazur and Rubin about the distribution of this. So Mazur and Rubin were interested about the non-vanishing of object of this form, of a multiplicative twist. Okay, here at the central point, here it doesn't converge, but as usual, it takes an anti-continuation. And before I said, okay, we can decompose this in Dirichlet character, they kind of did the opposite. You decompose these in exponentials and in additive character, and then you try to understand the distribution of these objects here and try to deduce the result about this. So when doing that, Mazur and Rubin came out with this, and I think on this there was also no, maybe there is also a result, something very similar to it conjectured by Stein, and that they conjecture that if you take the probability, so this probability will depend on a certain parameter Q, that, well, basically that this behaves like a normal random variable, meaning that L phi of, at the central point, L phi of 1/2 x divided by the variance, and the variance will be log Q, and okay, there is a constant. So the probability that this belongs to a certain interval converges Q going to infinity, which I'll define in a second, to the probability, not depending on Q, that a normal random variable of mean 0 and variance 1 belongs to alpha beta. This is for all.
So with Q?
Yes, I'll define it now. So more than Q, I have to define this probability, and this probability is the uniform probability on rational x in Q, the other Q, and 0, 1. Again, 0, 1 is periodic, so every if you translate it, just get the same result. And the set of denominator equal to Q. So this was their conjecture. This conjecture is still open, but
denominator is a reduced fraction or not?
yes, the reduced fraction. Yeah, but reduced, but you can also do it not reduced.
And this is equal, it's not up to Q.
Yeah, exactly. This is the conjecture, but I got the red chalk. And in fact, for the actual conjecture, there is basically been zero progress. I mean, there are progress on the first moment, but which is known, but okay, it's way easier. But there has been quite some progress on this. So if you take less or equal to Q, which is easier. Like it's still not easy, but it's definitely easier. The one with equal to Q seems completely inattackable to some extent. Since continuous fraction were mentioned, this is also similar to the issue. Like we don't understand continuous fraction for if you vary over fixed denominator as the denominator goes to infinity, whereas we understand them fairly well if you let the denominator up to a certain point. These two things are related, and there is hardly any progress on this fixed case, on the equal case. Okay.
In this conjecture, is phi a holomorphic cusp form?
So, okay, to be precise, yes, their conjecture, they only made it for form that come from elliptic curves. So in their case, the conjecture is for k equal to 2, and well, phi cuspidal, or even coming from a elliptic curve, but okay, the fact that it comes from elliptic curve or not is irrelevant. The fact that k is different than 2 plays quite some role in the proof. It's much harder if k is different than 2. Well, I don't know. It's different, the problem. But the same conjecture holds. Whereas if you want non-cuspidal, then this is not exactly precise. You have to add a certain power of log Q. Where R is 0 if it's cuspidal, and 1 or 3 depending on on the case of in the non-cuspidal case. For d of n, r would be 3. For r of n, r would be 1. You have to add it here. Sorry, inside the square root, so it would be r.
It's still holomorphic.
Sorry, no, in general. Also,
Okay.
I mean, the conjecture is the same in all cases, with the only difference being this factor in a non-cuspidal case. And this was proved by Pedridis and Rizagé in 2018. And, sorry, not in general, but in the case that they stated, that is for k equal 2. And holomorphic. So this was 2018. Again, all here will be less or equal than Q, not equal. So their case was k equal 2, then any level, holomorphic, and cuspidal. And all of these, well, okay, these 3 assumptions were all crucial for their method. And so this was 2018. And then soon after, there were 3 results on this that came out a few months apart. They were independent and also all with different proofs. So one is by Lee. Jungwon Lee and Sun, that proved the same result with methods from dynamical systems. And then there was another result by Nordentoft, in 2019, with who removed this hypothesis with a different method that kind of cancel any hope of dealing with the cuspidal case, because you use the method of moments and which cannot handle the cuspidal case because the moments are Dirac for the high moments. And so for all k, for all n, also holomorphic and also cuspidal. Okay, so this was the first 2 results of that year. And just one. And then the same year, there is another result by Mr. Ansari. So that proves the conjecture in the case k for all k n equal to 1. So and then 2 more cases, holomorphic and cuspidal. So this is covered by the result by Norton, but different methods. And or in the case of an being the divisor function. And in fact, one can probably expand it a bit, but so this is a non-cuspidal case. Okay. And what is interesting about this method is that it can be generalized to also other non-cuspidal case and holomorphic case. And in fact, in the paper by 2022 that I mentioned by Draco and Nordentoft, they basically inputted this result here into our proof, and then deduce the case for all k n equal 1, and that's it. With removing the assumption that the function is holomorphic and cuspidal. And okay, the theorem, or the new theorem by myself, Sari Drapeau, and which I won't write again, and Jung-Won Lee. This is 2025 plus, more or less done, but never knows what else. It's also almost everything now. Then we can remove this assumption. So basically it completes the conjecture in all possible cases, cuspidal, non-cuspidal, and so on. Okay, so don't really have much time. I wanted to say something about the proof, but okay, basically nothing. I'll say something about the method. So the work by Petridis and Riesage and by Nordentoft use some basically some twisted Eisenstein series in Eisenstein series twisted by modular symbol, basically. Which were studied by Goldfeld, introduced first by Goldfeld, and they studied this object for what's needed, and they can deduce results from that. And whereas the result 2 come from a dynamical system, so more specific about basically continuous fraction. And in particular, they owe a lot on a paper by Valadi and Ballet on continuous fraction. I'm not sure about the accent, where it goes and how it goes, but the letters are correct. Okay, so and this is almost all the other case, with the difference with this, the last case is use dynamical system, but in a different way, like with a different method, not with directly with continuous fraction. So how does the proof work, like in one line of this? So basically one, okay, I'm gonna write it here. So basically one have that by this result here that was mentioned about this H gamma, one has that L phi of x is equal to H gamma of x in the n equal 1 case. Plus L phi of gamma x, and where by gamma, if by gamma I take 0 minus 1 1 0, this is minus 1 over x, and by periodicity, this one I can actually put the continuous fraction because L is one periodic. So basically, if one wants this one, well, it's just the same thing, is this the Gauss map at x. T of x is just the Gauss map. And if one iterates this, one gets that this one is h gamma, sorry, this is h, if you call this s, this would be hs. Or let's just call hs. So hs of x plus hs of minus t of x plus hs of minus t square of x, the iterated and so on. And so basically this is something that analyzes with dynamical systems and study with dynamical system method and these behave independently, t of x, more or less. And so one deduces the distribution. But this uses crucially the fact that these elements stay in the group. So it doesn't work in n different than 1. So, okay, I want to say 2 more things and I have hardly any time. Okay, so whereas about 1, the problem is that holomorphicity, there are 2 problems in extending it. The problem, well, one, holomorphicity is used crucially because one uses Cauchy's theorem quite from the beginning. And the second problem is that it uses the method of moments, as I said, which kind of cannot work in non-classical case. So, I conclude by saying that just one thing about the proof, which is just a little drawing. So basically, one has to use a different reduction algorithm than the Euclid algorithm. This is basically doing Euclid algorithm, the continuous fraction algorithm. And this is due to a paper in 1979 by Bowen, Rufus Bowen, and Caroline Sirius. Bowen died very young the year before this was published. So, so basically, if you take, okay, let's say that this model of the upper half plane, so, and then I quotient by gamma, so say that we can have something like that. I want in an ideal domain, which is possible modulo passing to some cofinite subgroup, which is okay for the application. And basically, so I'm here, and then, so this is the fundamental domain. And if I have, and say that with gamma 1 brings you back in, here gamma 2 brings you back in, here say that you have gamma 1 minus 1, so these sides are paired. Here say I have gamma 3, and here I have, say, gamma 3 minus 1, and here gamma 2 minus 1. So if I have a point here, then I apply gamma 1. So I have here this basically correspond to the real line, and apply gamma 1, and I end up somewhere in the border apart from this interval. So say I could arrive here, and I keep going. And what they proved is that it's a reduction algorithm. So, so basically, you eventually, if you start with a reduction, eventually you reach one of these 6 cusps. But then there are issues because, well, this is much more hard to understand this algorithm than the continuous fraction algorithm, and also it converges very slowly. So one has to accelerate it, which is something typical in the dynamical system, and prove a bunch of results about that. And then, okay, I don't have time to say anything about the proof, but and just write one more line, is that something also that we are proving is that one can also consider the real, the discrete, the continuous version of this. So instead of taking x real, we can also take, x rational, we can also take it real, truncated over Q and letting Q go into infinity. And for this object here, f of x, which has a finite sum, or you can truncate in other ways. This one also, as Q going to infinity, converges to a normal. Okay, thank you very much.